In this video, we introduce Rolle's theorem. Now, you would think, oh, it's named after a mathematician Rolle, so it should be a really important theorem. But in all actuality, it's really just a stepping stone to the mean value theorem, which is an incredibly important theorem in mathematics and calculus in general. But Rolle's theorem is our stepping stone, so we've got to start there first. And what it says is that suppose f is a continuous function and it's on the closed interval ab, so it's continuous. This is a hypothesis. It's differentiable on the open interval, and we have, and this is what makes it a very special case, that it's equal at the endpoints. Well, what Rolle's theorem says is that, well, if it's equal at the endpoints and continuous and differentiable, then somewhere in the interval, the derivative is zero. We have no choice. And let's kind of take a look at this. We know that it's a continuous function. And so we know from our previous discussion, extreme value theorem, that it's going to have a max. Let's let m be the max of f and little m be the min of f. All right, so this is the max. And then obviously max is bigger than the endpoints and the min is less than or equal to the endpoints. So this is our requirements, and we have, well, a few cases. Case 1. This is where m equals our endpoint f of a, but it's also equal to the min. So it's saying that the min and the max are the same and it's equal to our function. Well, the only way that could happen is a scenario like this, where here's our max and min value, m equals m, and our function then has to be constant all the way through. Right? If the max and min are the same, then I've got a constant function. This would be, our function has to be f of x equals m. Right? Well, what is the derivative all the way through here? Well, everywhere the derivative is zero since it's a constant function. So case 1, where the max and min are the same, the derivative is always zero. So obviously there is a value inside where, let's call it here c, where f prime of c is 0. Okay, that's one case. The second case is when, say, f of a is less than the min, or the max. And so is since we know that f of a is less than the max, then the graph would have to look something like this. So here is, say here's our max, here's where f of a is, and remember f of a and f of b are equal, so they're here. Well, the only way, so the max is up here somewhere. If it's continuous, then it's going to have to go up to the max, and it may come down, but it has to go up to the max, and what goes up must come back down to get to b. And so at this point here, at that point there where it turned around, f prime of c is 0. So that was case 2. Case 3 is saying that, let's say that the minimum is strictly less than f of a. And again, a graph where this happens could look something like this. So let's kind of in generality assume that this is where f of a is. And maybe the minimum's down here. And we know that f of a and f of b are equal. And so the minimum, the function's going to have to, it could start up, but then it's going to go down, reach the minimum, and then it's going to have to come back up to get to this value, which is f of a, because they're equal. Again, where it went down, that spot there, f prime of c is 0. So Rolle's theorem really just says that if the function is equal at the endpoints and differentiable and continuous, then the function is the derivative of the function is 0 somewhere. All right, so that's Rolle's theorem. Before we use it to prove the mean value theorem, let's just kind of quickly take an example where we could use Rolle's theorem. So let's show that if f of x is x minus 1 squared, x minus 2 on the interval, say, 1 to 2, that f prime is 0 somewhere in the interval 1 to 2. We're not going to calculate it. So we could take derivative set equal to 0, but all the Rolle's theorem, it just says it exists somewhere. It's worth looking. And so what is the requirements of Rolle's theorem? Rolle's theorem say that f has to be continuous, it has to be differentiable, and equal at the endpoints. So is f continuous? Yes. Is it differentiable? Well, this is, if I expand this out, we'd recognize this is a polynomial, and all polynomials are differentiable. So we can, just go through and make sure we're meeting the requirements. So f continuous, yes. F differentiable, again, yes. Does f of 1 equal f of 2? That's the third part of the hypothesis. Well, f of 1 would be 0. F of 2 would also be 0. So yes, they're equal. So by Rolle's theorem, we have some spot C so that there is a C in the interval 1, 2, so that f prime of C is 0. Now again, we didn't find it. We could. You have the tools, you have the techniques to find it. But what Rolle's theorem gives us is just a quick way to say yes or no without actually even calculating the derivative. As long as it's continuous on the closed interval, as long as it's differentiable on the open interval, and as long as the function is equal to itself at the endpoints, then Rolle's theorem can be used to just answer yes or no, the derivative is 0 somewhere in that interval. Now let me give an example, because oftentimes students way overuse Rolle's theorem. So let me ask this question. Does the derivative of f of x equaling 3 minus x squared, or x to the negative 2, sorry, on the interval from -1 to 1 ever equal 0? Right, so that's the question. So it's quite often that I'll see students go, oh, well, Rolle's theorem, I just have to evaluate at the endpoints and see that they're equal. And sure enough, if I do f of minus 1, well, it's equal to 3 minus 1 over negative 1 squared, so that's just 2. And that's the same as f of 1, which is also 3 minus 1. So they're equal. And a student go, oh, well, good, I can use Rolle's theorem and say, yes, the derivative is 0 somewhere, but you would be improperly using Rolle's theorem because that's not the only assumption. We have to know, is f continuous and is f differentiable? And in fact, this function is not continuous, nor is it differentiable, because at 0, f of 0 does not exist. If I put 0 in here, I got 1 over 0. That's not a value. So the function doesn't even exist at 0, so it's not continuous on the closed interval. And similarly, if I took the derivative here, f prime of 0 does not exist. Even if I didn't take the derivative, I know it's not continuous there, so the derivative can't exist either. So I've failed 2 of the hypotheses. It's not continuous and it's not differentiable on the whole interval. And so in fact, I don't know for sure. It still could be somewhere the derivative is 0, but Rolle's theorem can't be used. However, we'll learn in chapter 5 how to graph a function like this, and its graph, we've got an asymptote. Well, actually, you learned how to graph functions like this in college algebra, but nonetheless, we'll revisit this again in chapter 5, but we've got a discontinuity at 0, and the function will look something like this, and then like this. And so nowhere in this interval, I know I graphed it bad, but nowhere in this interval we'll find is the derivative ever 0. So just giving you that forewarning, don't fall for the classic mistake of just saying, oh, well, the endpoints are equal, therefore Rolle's theorem can be used. Rolle's theorem has 3 very important hypotheses. Yes, they have to be equal at the endpoints, but the function has to be continuous on the whole closed interval, and it has to be differentiable on the entire open interval. If any of those hypotheses fail, then you cannot say that the derivative must be 0 somewhere. It's quite possible that it could be, but in this example, as we saw, it's quite possible that it isn't.